Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue looking at problems that we can solve nicely using recursion, and in particular recursion that branches, so recursive functions that call themselves more than once. And in this video we're going to concern ourselves with a little game. It's the Towers of Hanoi. I guess you can call it a game. It's a logic puzzle in many ways. And so to make sure that everyone understands what this is, I've pulled up a little website here. It's called Math is Fun, and this shows the setup for the Towers of Hanoi. After seeing this, if you weren't familiar with what it was, this probably jogs your memory, and now you know what the game is. So you have disks of varying sizes, and you have three different pegs that you can add them to, and your goal is to get the tower of pegs from one side, from one disk to the other, or from one peg to the other. But the disk can only be moved one at a time, and you can never place a disk on another top of another disk that is smaller than it. So in the case of 3, we can play this game by doing something like this, and that moves everything from tower 1 to tower 3. You can increase the number of disks, you can decrease the number of disks. What we want to do here is write a computer program, an algorithm that solves this for us. Okay, so let's go in and let's make a file, hanoi.scala. And so there are a number of questions that we have to address in order to do this. One of the big ones is, how are we going to represent these pegs and these disks inside of our program? So for the disks themselves, all that we really care about is their size, and we can represent that nicely as just an int. So a stack of disks could be something like a list of ints. And a list works very nicely because, remember, you can pull off the head of a list and you can add to the head of a list very efficiently. For the 3 different towers, that basically means, so if I represent this by a list of ints, well then this is also going to be a list of ints. Right now it's an empty list of ints, and this is also a list of ints. It's also an empty list of ints. And these are going to change every time we do a move. And so instead of making this a list of ints, I'm going to make it an array of list of ints, because the array is mutable, and that way I can change the lists every time that a move is made. So let's go ahead and create a val. We'll call it pegs, and it's going to be an array of, and I'll start off here, I don't need to tell the first one that it's ints, but I want to tell the others just to make sure. This one will figure it out because 1, 2, and 3 are all ints. So this will create our pegs for us, and what we want to do is write a number of functions that allow us to solve this problem. And the first thing I want to do is I want to write a function called, let's call it move one disk. Okay. Now, when I call this function, I have to provide it some information. Okay, what information do I need to provide it? Well, I'm going to move a single disk, and it turns out that you don't really have many options here. You're only allowed to move the top disk from a given peg. So if I just tell it the peg that I'm moving from as an integer, so this would be peg 0, peg 1, peg 2. If I tell it what peg I'm moving from, well, it knows that the top peg, or the top disk on that peg, has to be the one that we're moving. And then I also have to tell it where we're moving it to. Okay. And what this should do is it should change the peg that we're moving from, pull off the top element, and move it over to the one that we're moving it to. So how could we do this here? Well, we can do this in 2 steps. Pegs sub 2 cons equals peg sub from dot head. So this takes the head, the top element, right here in this case the 1, of the thing we're moving from, and it conses that onto the thing that we're moving to, and because this is a cons equal, it then stores that value back in the array. So if I said to move from 0 to 2, that would take the first element here, this 1, and it would add it on to this list. Now at that point we still have a 1 here and a 1 here, so we then need to clear that off and say pegs sub from equals pegs sub from dot tail. Okay, so I want to make it so that it's equal to everything except for the head, which in this case would just be the 2 and the 3. Now, that function is technically sufficient for us, but I want to put in a check here to make sure that this can never happen in an invalid situation. So I want to require either that pegs 2 is empty, because if there's nothing there, well, clearly I can move whatever disk I want onto it, or that peg sub from dot head, the disk that I'm moving, is smaller than pegs sub 2 dot head. And I have to put these in this order. I have to do the check for is empty before I do this, because if it's empty and I try to call the head on it, it'll crash. So this places a requirement, and in fact, if we ever call move one disk and this isn't true, our code will crash. And make sure that our move has to be valid. And so I'm going to build the rest of the code so it always calls this function for moving. It will never do a move except via this function. Let's do a real quick check to make sure this works. I'm going to do a print line of pegs.mkstring, and let's go ahead and separate them. Let's just separate them by commas. And then I want to call move one disk, and as I described earlier, we can go from peg 0 to peg 2, and then let's run this. So we start off with all of the disks 1, 2, and 3 at the beginning, and then after this move, 2 and 3 are here and 1 is there, just to make sure that our error checking is correct. Let's try doing an illegal move. So if I then try to move again from 0 to 2, that would try to place the 2 disk on top of the 1 disk, and sure enough, that causes our code to crash. Okay? And with a message, illegal argument exception, requirement failed. So our require statement caused the code to crash, and that's exactly what we want. If we ever try to make an illegal move, we want it to crash the code. Okay. So we have a function that can do a single move. And now the question is, how do we move a stack from one peg to another? Now, when I say move a stack, I don't necessarily have to have it be the entire stack. I just want to move some fractional stack. So I want to move in disks from one peg to another peg. Okay. Now, let's go back and let's look at our game here. This is where the recursion comes into play. Okay. How do you move something from here? Well, if it's one disk, well, that's easy. You just take it and you move it from one location to the other. So that's our base case. If n is equal to 1, then I am simply going to call move one disk from 2. Else, well, what if it's not just one disk? What if we need to move 2 disks or 3 disks or 4 disks? Well, this requires a certain observation. So when I want to move this entire stack of 3, what I have to do first is I can move this piece to here, and then I would move the entire rest of the tower somehow magically. Let's assume that I can move, let's assume that I can move n minus 1 disks. So I have n disks. I move 1 over, and then I'd move n minus 1 across, and then I'd move that 1 over to the top. Okay. Now, this is we're doing a process here called induction, and a lot of times when you're writing recursive algorithms, you're doing this. The idea is that if I can show that I can do it for one element, and then if I can come up with a rule where if I can do it for n minus 1, I can do it for n, or alternately, if I can do it for n, I can do it for n plus 1, I can put those together, and then I can do it for anything. And so for n elements, a very general rule is move the first one to the tower that you don't want your stack to be on, then move the entire rest of the stack over to the tower that you do want your stack to, oh, sorry, never mind. I'm doing this incorrectly. Let's start off with move the n minus 1. So if I assume that I can move, once again, I have n disks, I'm going to assume I somehow have a magical oracle that will move n minus 1 disks for me. And so I can pick that magical oracle to move those n minus 1 over onto this tower. Then I would simply pick up this 1, move it to there, and then I would use my magical oracle again to move those to there. But if you apply this recursively, that magical oracle is the function that we're writing. Okay? And eventually it gets down to the level of just 1 disk, and then it finishes. So our magic oracle is this function itself. So in order to move n disks, the first thing I do is I'm going to move n minus 1 disks from the front post and then to the other post. Now, this is a question, how do we find the other post? Because we have a from and a to, but they didn't tell us the other. You could go through a big if that says, well, if from is 0 and 2 is 1, or if from is 1 and 2 is 2, etc. It turns out there's a very simple mathematical way to do this. Because when you add up the indices of the posts, okay, the posts are numbered 0, 1, and 2. And so when you add them all up, the answer you get is 3. So it turns out if I give you 2 of them, and I subtract those both from 3, the value that you're left with is the index of the third post. Okay, so if, for example, I was moving from 0 to 2, well then this says 3 minus 0 minus 2, which gives me 1, and sure enough, that's the other disk. So after I've moved n minus 1 disks from the front post to the other post, and notice this is a recursive call back up to here, then I move the 1 disk that's left to the 2 posts, and I'm going to do that using my function right here. I move 1 disk from 2. After I've moved that 1 disk, I move the stack of n minus 1 from other to 2. Okay. So move n minus 1 to the peg you don't want to have at the end. Then move the bottom disk all the way over to where you want things, and then move the n minus 1 to where you want everything. Okay. This is a simple application of a recursive function call, and we can check to see whether it works by calling move stack, and I want to move 3 elements from 0 to 2. Now note, this function here never actually changes the values of pegs. All of our changing is happening up here, and as we already demonstrated, this has a check to make sure we do it in a legal way. So if this ever tried to make an illegal move, this code would flag it and we would get an error. So if this works, well, then it actually does what we want. And so we start off with all 3 disks on peg 0, and we end up with all 3 disks on peg 2. We could make this a little bit more general. Pegs sub 0 dot length, and then change this to maybe something like 1, 2, 3 dot to list. And that way I could very easily change that to a 5, and then we can run it and see that it works. It's a very interesting question to ask, how many moves does it take to solve this problem? And the way to think of this is how this recursion branches off. So if I call this, for example, with 5, where my n value is 5, which is what I'm doing right now, well, then that calls itself twice with values of 4, and each of those calls itself twice with values of 3, and each of those calls itself twice with values of 2. So whatever n I'm passing in here, this function calls itself twice repeatedly until it gets down to just 1. That calling itself twice means that the total number of moves, because every time we do this, we move a single disk here, and then we also move a single disk at the base, is going to grow as 2 to the power of n. So the number of moves we do is exponential here. And in fact, so with the 5, there wasn't much of a delay. 15 is also fairly fast. 25, you noticed a pause there. Okay, it printed out the first set, but then it paused a little bit before it could print the second set. We'll just take one more step up to 30. Now, something to note, if you keep in mind that little rule of thumb that 2 to the 10 is equal to roughly 10 to the 3, that means that 30 is going to require on the order of 1 billion moves. And so even on a modern computer, and modern computers are very fast, 1 billion moves takes a while. You can see here that, well, this isn't going to finish immediately. Okay, there we go. So 1 billion moves was reasonable, but it was still slow. If you push this up much beyond 1 billion, you're going to hit the point where you're not willing to wait for it. So that's it for this video. What I want to do next is come back in the next video and animate this a little bit. Just a fun thing to do, help to reinforce some of our ability to write GUIs and graphics, and also hopefully seeing it animated out will help you to understand what's going on here in this recursion.